Fair word of warning, this is definitely introduction to ranges, so for the majority of people in here, I'm sure it's a lot of review. Probably more useful for the folks online, but there should still be some stuff in here for everyone. I'm going to start out by talking about arrays. Originally I was going to talk quite a bit more about arrays than I'm going to, but the talk was too long. But understanding the basic semantics of dynamic arrays can be fairly critical to understanding how ranges work, not only because ranges are at least partially based on the semantics of dynamic arrays in D, but they're one of the most common instances of ranges, and their semantics often seem a little bit weird to newcomers to the language, and even folks that have been using it for a while sometimes misunderstand how they function and end up with weird things they're not expecting. But I think the core thing you need to understand when you declare a dynamic array, like at the top, what you're essentially getting is at the bottom. It's a struct with a length and a pointer. In reality, I believe D runtime uses a void star. It's not really templatizing this thing, but semantically, this is what you're dealing with. And for the most part, the semantics you get with a dynamic array are exactly what you would expect from a struct like this. Essentially, there are overloaded operators and whatnot, so that, op equals is going to actually compare what the elements it refers to are, not the, shallow struct comparison. And you've got concatenation, some other things that are added. But particularly when you're talking about copying a dynamic array or slicing it, this is exactly what you need to understand what it's going to do. So when you slice it, it's just editing the length and, well, not editing because it's making a copy for the slice, but it copies the struct, and the length and pointer are just edited for that slice. So if you move from the end, the length is reduced, pointer stays the same. If you're moving from the beginning, then the pointer and the length change. Doesn't have to go to the GC, doesn't have to do any other operations. It's just messing with the pointer and length. And of course doing bounds checking to make sure the numbers you're given are valid, but the semantics are very straightforward, and what you get when you copy this thing is exactly what you'd expect from a struct. And in particular, quick example, if you pass an array, in the first example here, without passing it by ref, and the second one you pass it by ref, there are subtly different semantics. In both cases, if you edit an element, it's going to edit the array that you passed in. So in this case, I assigned 2 to the first element. But in the other case, the semantics for that are identical because the memory it's referring to is the same in both cases. However, in the second case where you're appending, if it was not passed in by ref, it doesn't do anything to the caller. This is only affecting the array inside this function because arrays aren't really reference types. They're not really value types either. Dynamic arrays are kind of halfway in between. I don't know if we call them a pseudo-reference type or what exactly, but with this struct, the pointer part is essentially a reference, but the length isn't. So when you pass it in, what you do to it, unless it's affecting what's pointed to by the pointer, is not going to affect the caller. Of course, in the second function, because you're passing by reference, it does affect the caller. And unsurprisingly, for the third piece where you're assigning a new array, in both cases, well, you end up mutating it in the first case and not in the second, and this is the exact same behavior you'd actually get from a class. So even if you're dealing with a reference type, that's more or less what you'd expect. But if you understand that this is what you're dealing with when you're dealing with a dynamic array, it will be a lot easier to understand. In particular for the additional semantics in terms of concatenation and things of that variety, the dynamic array really doesn't know or care what's backing it. It could be GC allocated memory, it could be malloc memory, it could be a static array. In terms of the actual semantics, the only real differences are how that memory is managed, and particularly how it's freed. If it's backed by a malloc array and then you foolishly go free it out from under it, you're going to have memory problems. Whereas if it was GC allocated, you don't have that problem. And the other big difference is, of course, when you append to it, whether it's going to reallocate or not is considerably different based on what's backing it, because if it's backed by malloc or static array, malloc memory or static array or whatnot, then it's going to have to reallocate. Whereas if it's backed by GC allocated memory for dynamic arrays, it depends on whether it has space to move into without having to reallocate. But the result of all this is that dynamic arrays, while they're kind of containers, because you can append to them and they kind of seem like containers that way, they really don't own or manage their memory. Particularly if it's a slice of malloc memory or static array, it's not doing anything for the memory management. You had to have dealt with that elsewhere. And there's no GC anything going on when you're slicing an array or passing it around. It doesn't keep track of any of that kind of stuff. It really only deals with it when you deal with capacity and appending and things of that variety. And I think frequently people misunderstand dynamic arrays and think of them as containers, which they kind of are, but not really. And in particular, in the case of ranges, if you're thinking of them as containers, you will be confused. And just quick word of warning, if you're dealing with a dynamic array that's backed by something other than GC allocated memory, make sure you don't do something stupid that results in the memory no longer being valid. Particularly static arrays, when they're sliced, become dynamic arrays. And if that static array goes out of scope, it doesn't exist anymore and you're in trouble. This actually becomes a big problem with ranges if you're not careful, because it's very easy to hide the fact that it was a static array originally once you sliced it and start passing it to a bunch of different functions. And unfortunately, at the moment, it's actually considered safety to slice a static array, even though that's semantically identical to taking the address of a local variable. So that's a bug that needs to be fixed at some point. And unfortunately, though I doubt we can fix it at this point, static arrays do implicitly slice as dynamic arrays. So if you're not careful, you can end up passing a dynamic array around that you thought was GC allocated, and it wasn't. So just in general, if you're dealing with static arrays, with ranges or not, but especially with ranges, you need to be careful. Okay, briefly, iterators, since this is what C++ and Java and everyone else is using, and is arguably the basis for coming up with ranges. Classic thing in C++ is you're going to be getting two iterators from a container to iterate over the contents. You get the begin iterator that points to the beginning, end which points to one past the end. And the STL is wonderful in that there's lots of functions you can pass these iterators to and generically manipulate things. In this case, find is a generic function, which takes the two iterators and the value you're looking for, and then you can determine whether you found what you're looking for by comparing the iterator with the end, the resulting iterator with the end. And you can reuse these iterators because they don't always have to point to the beginning or the end. So in the second example here, it reuses the iterator effectively to search for something else. So iterators can be moved around, don't always have to point at the beginning and end of containers, so that they are a lot more flexible and can be reused in various algorithms. And technically they don't even have to be backed by containers, even though in the majority of cases with C++ they are. But iterators are essentially abstraction for pointers. Most of their behavior is similar to pointers, and a pointer is an iterator. They only ever refer to a single element, so when you're dealing with something like find, all the C++ stuff, you have to pass two iterators all the time. The result of that is you have higher risk of issues because if you pass them out of order, you have undefined behavior. You don't want to pass end before begin. And if you pass them, they point to two different containers, but the same type, you also have undefined behavior. So while they're very useful, they are somewhat error prone. And particularly in comparison to ranges, the big problem is the iterators are very unwieldy for chaining algorithms. As useful as the STL is, because you always have to have two iterators, it becomes a lot harder to take the result of one function and pass it to another. You can't simply chain them, you have to keep getting end and passing the appropriate end to the next function. And if end was moving as well, you're gonna have to pass a pair back or take it by reference or whatever. It gets more complicated. So it's doable, but it's a lot more unwieldy. Same code with ranges. In this case, we've got a list that's being sliced. So a container, when you have a container, the way you get a range from it is to slice it, at least with how it's defined in standard container. So this is giving you a single range. You're now looking for that value. And to check whether you got the element, you check the empty member of the range, at which point you can reuse the range in the exact same way you're reusing the iterators, except you're only passing one value around. So semantically, this is pretty similar, but slightly simpler. And ranges essentially are an abstraction for a dynamic array, sort of. They don't have concatenation and things of that variety. And there's enough range, well, bad word, there's enough variety in how you can implement ranges that they don't all have exactly the semantics you'd expect from a dynamic array. But the basic idea, I mean, a dynamic array could be viewed as two iterators. It happens to be implemented as a length and a pointer, but it could have been implemented as two pointers and have the same semantics. So essentially two iterators. And a range is essentially, at its most basic level, two iterators. So instead of passing begin and end, you passed one object that contains begin and end. So now you're only passing around one object, and when you return from find or whatever your algorithm is, it's really easy to chain it because you only have one object to worry about. There are a variety of different range types, similar to the variety of iterator types in C++. Like not every iterator in C++ can have the decrement operator used on it. Not every iterator can, have 7 added to it or whatnot. They're not all random access. They're not all bidirectional. So we have essentially the same set of general separation and hierarchy with D ranges. The most basic, of course, is input ranges. And this particular template is input range, is what is used to determine whether a type qualifies as an input range. So there's a piece of code in the middle there that basically has to compile for this to work, and there's some extra muck around it you probably don't want to worry about. So the simplified version thereof is this. So you have to be able to declare one, basically. It has to have an empty member that indicates whether or not the range is empty, because that's going to be used for determining whether you're done iterating over it. It can be implemented as a function. It can be implemented as a variable. It can be implemented as an enum. It just has to compile with this line of code. Now, semantically, what all the code's going to expect is that this tells you whether the range is empty or not, but we can't actually test for semantics here, unfortunately, just the syntax. The next function that it tests for is popfront, which is equivalent to incrementing an iterator. It pops the first element off of the range, as opposed to front, which is equivalent to dereferencing an iterator, so you get what is currently the front of the range. So an implementation, in this case, based on the idea of iterators, here we have a templatized struct, which is templatized on the iterator type, and it holds two iterators. And front is dereferencing the first iterator, and empty, it's empty when the iterator and end are equal, just like you'd be seeing in C++. And popfront's just incrementing the front iterator. So this is a fairly straightforward conversion of what you see in C++. Now, while it's nice to think initially of ranges as being based on iterators, all it really requires is these set of functions. So there's all kinds of things you can implement that have nothing to do with containers, nothing to do with iterators, that follow this API and are extremely useful. They basically, by giving you a range of values from somewhere. So here's another example. It's also an input range, and it just counts to 10. Not terribly interesting. But as you iterate through, front goes from 0, 1, 2, 3, up to 9, and when it hits 10, it's empty. So if you were to iterate through this and print it out, you'd print out 0 through 9. And this has nothing to do with iterators, but it's following the same API. Now, this is probably more like what you'd want to write if you were doing that for how we normally handle ranges, by wrapping it in a function and using a Voldemort type. You get a lot more better encapsulation that way, and it allows you to do a number of more complicated things as well. It's just nicer, allows you to chain algorithms frequently, since in a lot of cases, the algorithm would be taking another range with some other arguments as opposed to just an integer. But this does semantically the same thing as the other guy, except it's using a Voldemort type. Input ranges are the most common way to implement user-defined ways to use for each. Indeed, there's also op-apply, which is still needed for some types of cases. But in the vast majority of cases, you're going to be using a range. So, top code, you're iterating over this range, getting the elements. If you use count to 10, this is going to iterate, give you 0 through 9. That gets lowered to the code below. So, essentially, it's just taking that range, iterating through it, and giving you that element. So the compiler understands ranges to the point to be able to use them in for each like this. I believe from what Walter was saying earlier, this is really the only thing the compiler understands about ranges right now. But this is incredibly useful. This case, we're doing the same thing, but with a list again. First piece, you're getting a range from this list. Now you can do whatever you can do with ranges with this list, with this range from the list. But you can also use the list directly in for each. Like the most obvious way would be, is in the second piece here, where you just slice the list, so you get the range and iterate it over. However, the compiler does understand using the slice operator to get a range. So if the container itself is not iterable, it will see if it can slice it. If it can't, you're going to get a compilation error. But it will then attempt to slice it and give you a range so that you can iterate over your container just by putting it in the for each like so. I was saying before, dynamic arrays or ranges. And obviously dynamic arrays don't have front, pop front, and all that fun on them natively. However, standard.array does implement these as universal function call syntax functions so that you can use them, which does have the annoying side effect you pretty much constantly have to import standard.array. And some people have suggested that maybe we should move them into object. I don't know, but either way, they're currently in standard.array. And if you import that, you can now use an array as a range. However, as I was trying to make a big deal about earlier, dynamic arrays are not containers. So while they do support the slice operator with no arguments, a dynamic array is something you're iterating over. You don't really iterate over a container as an object. You wouldn't declare a container to be an iterator in C++. Most people consider that to be nonsensical. However, it pops up far too often in the forums that someone has tried to declare a container as a range. And really, it's the same thing. They're separate entities. You can think of a dynamic array as a view into a block of memory. So a range over a container is a view into that container. And generically, a range is a view into a list of elements of some kind. How they're generated depends on the range. Static arrays, however, while they could arguably considered containers because they do own and manage their memory, are not ranges. It's impossible to call a pop front on a static array because you can't edit how long they are. You can slice them, as I was discussing earlier, to get a dynamic array and therefore iterate over them, but then you have all the concerns of safety with that, which is fine to do. You just have to be sure that you don't leave the dynamic array that you sliced or any range that wraps around it longer than the static array is around, because if the static array goes away, then you've got memory corruption. And another note is that opslice with no arguments is a container function to support ranges. This is not a range function. None of the range traits say anything about opslice with no arguments. None of them require it. So it is incorrect to declare a range as having opslice with empty arguments. There's actually a bug that was reported recently because ref range and standard.range, unfortunately, my fault, does declare said function. And that's actually causing problems with for each because it's slicing it and ending up with a copy when it wasn't supposed to. And I believe there are a couple other places in Phobos where we have mistakenly declared opslice with no arguments, so we really should fix that. But in your code, don't do that except on containers, because the purpose of opslice with no arguments in terms of range-based functions is to give you a range over whatever you're slicing. And of course, concatenation and appending are not range operations. Really, slicing is what you're thinking about when you're using a range. You have this window, and it is shrinking as you iterate through it. You never grow it, ever. It is only shrinking. And here's a fun little example, one of my favorites. It's actually the same code 3 times here, depending on your poison. The first one does not use universal function call syntax. The second one does. Both of those would be on one line if it wasn't a slide. And the last one breaks it out so it is a little more legible. But this code is something that I don't think much of any other language can do except maybe something like Haskell in one line. What this does is rangen returns a random number generator that is an input range, an infinite input range, so it's never going to be empty. But front is the current random number. Pop front calculates the next one and sets front again. So you can now feed a random number generator to whatever function accepts ranges. If you're stupid, you pass it to for each, but you can pass it to any function that takes ranges, and as long as that function operates lazily, you're fine, because it's not going to try and eat the whole thing and hit an infinite loop. And the majority of functions in Phobos that are range-based do operate lazily. The ones here definitely do. So rangen is then passed to map, which is then going to take the element and convert it to something else. So rangen gives you longs. So it's a range of longs since you get the full value for random numbers. But we want ints in this case that were less than 100. So you modded it to 100, cast it to an int, and now what comes out of map is a range that's wrapped. It's not what comes out of rangen anymore. That's a nasty template type you never want to see. But it then is a range of integers from 0 to 99. Also infinite because we haven't done anything to make it non-infinite. Take, then, yes?
I should pedantically point out, before anyone online does, that that's not a random integer between 0 and 99 because of subtle issues with that are not about the random generator used, but have to do with the math of dividing by 100 to obtain random numbers. So you may want to use uniform there with arguments instead of just dividing by 100.
Okay, I'm not an expert in random numbers. Joseph's going to talk about that tomorrow. Either way, well, maybe it doesn't give quite the numbers I was saying. The concept is just fine. So you're going to get a range of semi-random numbers at least out of this. Take, in this case, will then take the first X number of elements off of a range or up to those number of elements if it's empty. Take exactly will take exactly, but take takes up to. In this case, since it's infinite, we're guaranteed to have 10 elements. And so now we only get 10 elements instead of infinite. And when we pass it to array, we then get an array. So in one line, we now have an array of 10 random numbers. Whereas in pretty much any other language, you're going to have to do some fun stuff with loops and seeding and other things I don't want to bother with. So I think this is a neat little example of how you can chain seemingly unrelated stuff to generate something useful in very concise code. And in general, it's frequently the case that someone's like, oh, Phobos doesn't have a function for this, does it? I don't know how to do this. And someone's like, oh no, if you use this function in standard algorithm like this, it will actually do that too. So most of the time, if you're looking for a range-based function that does something, if you look through Phobos and you think it through, one of them will probably do it for you already. Sometimes it's just a question of thinking of the name differently. Like, instead of drop until, You can have find. They do the same thing. It's just the name is find and not drop until. So maybe a functional guy would think drop until, whereas a more imperative guy would think find, but they do exactly the same thing. So if you can just recognize that, then you've got what you need. Here's a second example that I don't think I have time for, but it was doing other fun things. But as I was alluding to earlier, there is no way to unpop an element in ranges. You are shrinking the window. You are only ever shrinking the window. You cannot increase the size of the window. The other fun bit that I don't think we think about enough is that the semantics of copying ranges are undefined. What I mean by this is in this example here, I'm dealing with a reference type range, a value type range, and one that's a pseudo-reference type. Right? So maybe it has some members that are references and it has some members that are values. In the first piece here, second ref, is the exact same range as ref range. So if you start iterating over second ref, you're iterating over ref range. However, in the second case with the value type, if you start iterating over second value, you're not iterating over value range. It didn't affect it at all. Whereas in the third one with the pseudo range, it depends entirely on how it was implemented. In the case of arrays, even though they're more or less a pseudo-reference type, it actually acts more like a value type for this. However, let's say all you did was front is a cached variable. So you've saved front. Well, the copy, when it starts iterating, even if what it points to, like say a socket, keeps being iterated through, front stayed the same. So if you're iterating through second pseudo, and then you try and do anything with pseudo range, the first element is that old front. And then the rest of the elements are wherever you were in the socket, and actually you probably skipped an actual element in the socket because you read the old front and then it iterated instead of the one that had been saved in the other range. So you have the same, in this case I just saved them over, so now we don't have to worry about, at this point ref range is back to being valid, certainly in value range and pseudo range, regardless of how you iterated, because you assigned the copy over again. Now if you pass into a function, you have exactly the same problem as you did with the first three lines, unless you were taking it by ref. So what this means, and I don't think we do a good enough job with this, is that anytime you pass a range to a function, or assign it to another variable, you cannot use the previous range again unless you assign it another value. You can get away with it if you know how that particular range is going to behave, but in generic code, you don't know. And part of the problem we have is that most of the ranges we define are dynamic ranges or structs that wrap them, and they all have similar semantics, but the corner cases then shoot you in the foot. So a key thing is making sure you test your range-based algorithms with, say, reference types. I believe there are likely going to be a number of Phobos functions which fail miserably. We fixed some of them, but it's something that's frequently not handled properly. And I think this is something we generally do not understand as a community well enough. When you copy a range, you use the copy, you don't use the original anymore unless it's assigned a new value. Now, beyond input ranges, we have forward ranges, which are essentially meant to solve the unpopping problem. So this is the full thing, and this is the part we really care about. This is how the documentation shows it. So a forward range is an input range with a save function, save member. I'd point out that for whatever reason at the moment, it's required to be a property function. It is the only case right now in ranges where it's required to be a property function, even though conceptually it's not a property function, it's a function. So I think Stephen has a pull request open at the moment to fix this, and because we don't have strong enforcement of properties right now, we can probably change it without actually breaking code. But for whatever reason right now, you have to declare that as a property, as weird as that is. The others, it's optional. You just have to make sure you use them without parens in the case of front and empty. But what save does is give you a copy of the range that is a copy of the range without messing with the previous guy, with the original. So that now you can iterate over them separately. They're going to have the same results, all right? And in the most common case, you're dealing with a struct, and you're pretty much just copying it by returning it, such that it seems kind of like a worthless function. However, if you implement a forward range as a class and you don't have save, it's not going to work right because it's a reference type. So you are forced to declare save and return a new value, which likely means allocating on the heap, which was one reason not to use reference type ranges unless you actually need them. I've run into cases a time or two where I did need them, which is why ref range exists in the standard library. But in the vast majority of cases, you don't want to be declaring them. And in the vast majority of cases, we don't declare them, which is why we don't actually test for them well enough. But you do have to be concerned about them when writing your code. So in this case, we've saved the original range so that when we iterate over range, it doesn't affect orage. So if we pass it to equal, the equal function will iterate over the two ranges and verify that they're equal. Notice we saved on both of them because if range is a reference type, equal will eat the whole thing and it will now be empty. I think we frequently forget to use save in cases like this because we're dealing with arrays where this is not a problem because when they are copied, they are implicitly saved, as are a lot of the structs that wrap them that we use. So frequently, we're not using save when we should. And really, the only way to fix that is to make sure you test your code with reference type ranges. As you can see, if we pop elements off of range, it doesn't affect the original. Still has exactly the same elements. So if you're iterating through and you need to be able to back up, you need to save that range and then do whatever you're going to do, and then you are then going to take the saved one and reassign it over to the one you're actually iterating through to be able to back up, since you can't tell it to back up. And this is only going to work on types for which is forward range is true because they have to have save. So you can have input ranges that are completely unsavable and you can't back up, which is why we then have these traits like is forward range and is input range to be able to test on functions with the template constraints to verify that they will work with the type in question, that they have the properties and functions that you expect when you're in your implementation. Yeah, like I was saying, save is basically like slicing with an array. You're getting a copy that is in the same state and can be iterated separately. And we do forget save calls way too often. In reality, I think if we actually use it correctly, save is littered through the code and looks ugly. But the reality of the matter is, if you're not doing it in generic code, as soon as anyone tries with a reference range, it's not going to do what you expect. Even just using for each is going to eat your range. But because most ranges are dynamic arrays or structs around dynamic arrays or value types that were structs, like in the case of count to 10, we screw this up frequently. So testing is really the only solution, I think, to solving that problem. Fortunately, we have good unit test facilities, that we do need some better stuff in the standard library for support for testing various types of ranges. I think some work has been done on that recently. I was working on it at one point, never got around to finishing. So one or more of us needs to get that in there so that it's easier for all of us to test ranges. Very quickly, bidirectional ranges is the next one in the pack. The shorter version is basically, it's a forward range, only it also has back and pop back. So you can get stuff off of the other end of the range. Which means, for instance, it's not going to be infinite. But like an array is a bidirectional range. So it's able to pop stuff off the back as well as the front. And there are algorithms for which this is required. But as I was saying, we have different template traits for testing each of these various types. And so if you're writing a function, there's a range-based function, you're going to use that in the template constraint. This is one of the overloads of find, the simple one, that just takes a range and looks for an element within that range. It also takes a predicate as a template argument if you want to not use equality. But the key thing here is you can see it is input range bang R, because it's testing the type of the range and verifying that it is indeed an input range and didn't pass it like int. Since that's not going to compile and work with the code, so the template constraint saves you from getting weird compilation errors inside the template. Question?
Why can't a bidirectional range be infinite?
The vast majority of cases it makes absolutely no sense. I believe it has been pointed out previously that there are some weird cases conceptually where you could have an infinite range, be bidirectional. As far as Phobos is concerned, it is not possible. If I remember correctly, the traits actually, the way that the test is done, it doesn't allow for it. And when it came up last, we basically decided the complication was not worth it because it was in a corner case that really isn't going to happen. I mean, yes, conceptually, there are some weird cases where it could be done, but in the vast majority of cases, it's something like a random number generator where there is no other end. It makes no sense to have another end. So, in any case, the result of this, of course, is that range-based functions are basically always templatized. So if using ranges, using templates very heavily, which is scary to people at first, but really isn't that big a deal ultimately, I think. The main problem is interacting with classes and declaring functions on there because those aren't going to be virtual. There are some classes or interfaces, I forget which, declared standard range for input range, forward range, etc., that you can then derive from for a class that would do all this if you really need to do it on a class and be able to return from a virtual function, but that's not frequently done. There are a variety of other range types that I won't go over all of them. The first four are really the ones you're going to use. Normally the others are for more complicated cases where you need to swap or move semantics specifically. Element type specifically gives you the element type of the array. So if it's, an array, but of a range. So if it's a range of integers, that's going to be int. Has length just tells you whether there's a length member, and that can be used. Has slicing determines whether you can slice the range with indices, not empty. So you can say, I want 1 to the end and take out the first one, or 1 to the 7th element or whatever, and get a range that then is over those elements. And is infinite determines whether the range is infinite. And it does that by determining whether empty is known to be false at compile time, usually by declaring it as an enum. You can, of course, technically declare an infinite range that has empty as a function and just returns false, and that's not going to get caught, but don't do that. Phobos can't help you and prevent you from using it in stupid places if you do that. As a quick example, with integer array, element types int, it has length, it has slicing, and it's not infinite. On the other hand, if we passed such an array to filter, which is then going to give you only elements from that range that pass the predicate, in this case less than 42, that's still an element type of int, because the type didn't change with this one. But it doesn't have length, because it doesn't know how many elements are really going to be in there until it iterates over them. And filter is lazy. The only way it can know ahead of time is if it were eager. And it doesn't support slicing, again, doesn't know how many elements it's going to have. And it's not infinite in this case because the range it's wrapping is not infinite. If you try to filter random numbers, it would be infinite. And an example on the bottom for if it doesn't have length, you can iterate over a range with walk length to get the length, which of course you are going to want to save unless you want to eat the range. And in the case of containers, like a doubly linked list that don't define length, that's how you get their length.
I just want to expand on that a little bit. If you create like a linked list array or a linked list range, don't be tempted to put a length property in there, because length is kind of assumed by the algorithms to be like of order 1 complexity, and you can get into all kinds of trouble if you have something like that's ON complexity and yet call it length.
Yeah, the standard container actually has a list of complexities at the top, listing what the complexities are. Length, I think for some reason in there isn't O of 1, it's like n log n or something, which I think should be fixed, honestly, but log n? I don't know, I haven't talked with Andre about it, so I don't know the details. I would have assumed it would be O of 1. Either way, we basically require that length be essentially O of 1 or close to it, so that you're not having to iterate through everything. You want to iterate through everything, use walk length to count. Very quickly, random access range. You probably can't read that, but that's the actual template. It boils down to, it's either a bidirectional range or it's an infinite range that's forward, since you can't be bidirectional and infinite, which point it makes sure that it has the appropriate slicing semantics. And if it isn't infinite, it has to have length. So that basically this is set up to make sure that you can go to a particular index like you would with an array with the appropriate semantics. I don't remember why hash slicing isn't part of this, but it's not. So we actually have to check those separately if you want to be slicing ranges. The part at the bottom that I'm not showing you has to do with the opt dollar. Both hash slicing and random access ranges verify that opt dollar has the correct semantics if you declare it. However, because we added it later in the game, it's not actually required, which means you technically can't use it and assume it's there. There is an open enhancement request to make it so that if length is declared on the range, that can be generated for you. But there were some implementation issues thanks to associative arrays also having length and making no sense for this, that actually hasn't been finished yet. And quickly, very quickly, I'm going to go over strings, which are a bit of a sore point with many people. I certainly do not have time to give Unicode enough of an explanation to give it justice. But the key thing here is the char, wchar, dchar are encodings. They are not full characters. They're pieces of characters. In the case of char, I believe it's something like 1 to 6 chars makes up a code point. Wchar is 1 or 2. Dchar is with UTF-32, a code unit and a code point are actually equivalent. So a code unit is a bunch of pieces of a code point. The code point, you basically have a whole character in terms of like, you would recognize it as such, or it's a modifier on one. So you could have E, but then accent as separate. And those are really supposed to be one character when they're displayed on the screen. But for that, you need a grapheme, which combines code units and code points and gets into issues of normalization and all that kinds of nasty fun. Unfortunately, when the range stuff was introduced, Andre didn't know about graphemes. He thought that code points were as big as you got, and so he tried to make it so that it was more correct by default, a bit slower, but more correct by default, and faster if you worked at it, so that we'd have fewer Unicode issues, which I think was a good goal, but because graphemes exist, it doesn't really work. In particular, it results in some weird stuff going on. These are 3 examples of Unicode strings. In the first line on each, it's a char string. The next is wchar, and last it's dchar. And there's a considerable difference in their length. As you notice, length is the number of code units because it's the number of chars or wchars or whatnot, not the number of code points, nor the number of graphemes. However, if you use walk length, they're all the same. The reason is that PopFront and Front and company do auto-decoding for you. So they will give you a dchar, which arguably increases correctness, but doesn't actually give us the full correctness. And it means that string and wstring are what we call narrow strings. And ranges consider these strings not to have length, or slicing, or random access, because doing so could cut through the middle of a code point. This results in a lot of functions in Phobos being special cased on strings for efficiency purposes, so that they can actually use these operations correctly. We also have element encoding type so that you then know what the actual type of the elements are, even with narrow strings. Everything else it does the exact same thing as element type. In the case of element encoding type, it gives you the actual character type. But element type for all strings gives you dchar. Yeah.
Just a comment I make. Well, so this is a great opener for the discussion this afternoon, where essentially I'm going to be destroyed. But just to kind of preface my take on this, I think it's okay to have specializations in the standard library for strings for the following reason. As far as when it comes to string manipulation, treating them as a unit, relying on well-optimized library calls seems to be a recipe for success in virtually all languages. Handling them sort of one byte at a time and messing with them is okay in some cases, but those are rare enough that you can actually say, well, we're going to rely on those folks knowing what they do. As far as I'm concerned, I think going the route of powerful, good standard library functions that are specialized and optimized, I think is the best way to go.
Yes?
Could you just quickly slip back to the walk length one?
Yes?
Yeah. The situation, of course, is even worse than that because you could quite easily get those done with combining characters, and then you wouldn't even get the same lengths with walk length.
Except walk length says dchar.
Yeah, but with combining characters, you
Well,
could
yes.
have something that looked the same but would give you different lengths for walk length. I just want to point out for other people who might have seen that and gone, it's all right.
Wouldn't that only be when you deal with graphemes?
Yeah, but it would look the same on the screen.
Yes, but
the-
walk length uses dchar code points, not graphemes. So
Later.
either way, the whole thing's overly complicated. And unfortunately, to really use this correctly and have fast code, you actually need to understand a good chunk of it. One of the problems with what we've done with making them all dchar is that walk length does not do the same thing as for each. For each, in this case, which is just counting up, is going to give you 45 for this because that's the number of code units. Whereas walk length gave you the number of code points. So we have a dichotomy between the language and the library in how it functions.
If you go for each dchar C,
Yes.
then it will give you the
Which
code
you then have to do. However, you then have the problem of having to do things like element type and things in there because it's going to be inferred incorrectly in the case of generic code. So I'm really out of time here, but you really should be looking at bytecode unit and bychar and friends to get ranges of chars and whatnot for your code if you want to be.
Can take like 7 more
Efficiency.
minutes.
7 more minutes?
Yeah.
Oh, okay. Well, Walter's been trying to fix this problem on some level and add bytecode unit and bychar recently, I believe. So these are specifically for iterating over code units, or bytecode point, then specifically iterates over code points, and bygrapheme from Standard Uni will iterate over graphemes. So if you really want to handle this all correctly and efficiency, you probably want to start using these. One of the core problems with the auto decoding is there's a lot of cases where the auto decoding is completely unnecessary, and while functions like find actually can completely avoid it thanks to the specializations and just compare things at the code unit level, once you pass it to something like filter, it goes to dchar. And granted, even if strings are ranges of char, you would have to be concerned about the fact that you probably didn't want to pass it to filter that way. Maybe you wanted to use grapheme instead. On the other hand, if you're using ASCII, and only ASCII, then as code units would have been fine. So even if strings were not considered to be ranges of dchar, you would have to consider those kinds of issues when using functions like filter so that you didn't like chop up code points or chop up graphemes. But a serious downside to a lot of this is particularly ASCII code ends up being less efficient when it's unnecessary for that to be the case. And I think the majority of the core devs wish that we were not treating these as ranges of dchar and have decided that it was a mistake, even though many of us were on board with it initially. And we may or may not be able to fix it. There are certainly ways to do so with deprecation paths, but I'm not sure any of them are clean enough. And someone probably has to figure out how to convince Andre that it's a good idea, which is a whole other ballgame. So we may have discussions about that later. But for now, I would suggest looking into code unit and code point and things of that variety and reading articles on Unicode. If you haven't, if you're only dealing with ASCII ever, then you're probably okay. A lot of the stuff will just work correctly, even if you're searching for ASCII. Like find with ASCII, filter with ASCII, and things will naturally work correctly in most cases. But it is an annoyingly complicated issue, and our attempts to make it so you don't have to worry about it unless you really care about efficiency have harmed efficiency and not really made it so you didn't have to worry about it. So it's a complicated issue and something that people frequently run into when they start using ranges. Quickly over some common range functions that people use all the time. I'm not sure I'm going to list what they all are, but chain is used for combining two ranges so that they're now sequentially one range. Drop will return a range where the first element was removed. Iota is a function that many people don't like the name. I don't really care. The name apparently came from C++, but it generates a range of numbers. So you give it 0 and 500, it's going to count from 0 to 500. Similar to the count to 10 stuff I was doing earlier there. So it is a very useful function, but its name doesn't say anything about what it's doing. So it's not necessarily immediately obvious. Lockstep is particularly useful if you want to be able to have indices with for each, since ranges don't get indices with for each. They just get the element. And lockstep will allow you to then use iota with it to generate indices, so you can have indices with for each. Retro reverses a range, so if it's a bidirectional range or greater, it now flips it around, so you're operating on the back as if it were the front. Stride allows you to iterate through multiple elements. Skipping them. Take, as we went over earlier, is pretty vital for being able to take off the front of a range when you don't want the whole thing. Pop front end just pops several of them. Standard array has various functions that are very useful. The main one you're going to care about is array, because it turns a range into an array, which can be pretty critical for stuff, especially if you want to save it somewhere. So you can use type of on a range type to be able to declare a variable of it, even if it's Voldemort type. Standard algorithm is chock full of stuff. It's the main place to go, but in general you want to go to standard algorithm, standard range, standard array. Those guys, if you're looking for range-based functions for random stuff. So there's a number of useful functions in here, like find, starts with, until, sorts in there. Sort is one, for instance, requires a random access range, so it tests for that. And if you try to give it a string, string is immutable anyway for the elements, so it wouldn't work because it has to move them around. But even a char array would not compile with sort, which confuses some folks. But in particular, one thing to keep in mind, if you're looking for string algorithms, increasingly, our algorithms don't care about strings. They're generic, and so they either operate on arrays specifically or on ranges in general. So if you look in standard.string for everything, you won't find things. There are a number of useful functions in standard.string that are string specific that will do what you want, but algorithm, array, and range are frequently where you need to look. You had a question? No, just hand. And one last quick tip. One place that ranges fall apart on some level is handing them back to containers. In C++, this is fairly straightforward. You do a find to get the element you're looking for, and then you pass the iterator back to the container to tell it to erase it. And you don't have any type issues, and you don't have any issues of trying to delete too many elements at once. Well, as shown in the first bit here, you looked for 42 inside of the range from that list. If you passed that range to remove in the list, not only did you remove 42, you removed every element after 42, which is not what you want. In some cases, you can slice the range to get what you want, like with the capital A array type, which is similar to vector in C++. That is random access, so you'd be able to slice it, but in a lot of cases, like with a doubly linked list, you can't. So take allows you to take the first element, or X number of elements, and remove it and pass it to the container, but the container had to be specialized with remove to watch for that. So in general, you can't chain a bunch of ranges and then expect to be able to use that to remove from a container. At which point, I'm not really going to go over output ranges because I don't have time, and increasingly, the message is use lazy input ranges. There are cases where output ranges are useful, though I think they're underdefined. word of warning with arrays, they fill them, whereas with appender and various others, it appends to them. So using them generically can be a bit iffy, and there's no way to determine whether the put function, which is the main thing used with an output range, is going to succeed. But an output range, at least conceptually, is the opposite of an input range, where you're putting elements into it instead of taking them out. So questions in whatever minuscule time we have left.
Two questions. One, if you go back to the definition of, well, the test for is the output range.
Yes.
Why is that in out in equals 0 in there? Because I asked on the forum and nobody knew.
Okay. It has to do with supporting in-out. I don't remember the exact explanation, but I believe pretty much what happens if you're in a function where the range was taken as in-out in the parameters, then it's either the range itself or all of its elements are in-out. And it's not going to be in-out without this fancy little muck here that most of us don't understand. So if you run into in-out problems with some of your templates, maybe you look this up and ask some people about how to do this. Kenji figured this out and added it. Okay, Stephen will explain it to me.
All right, because I cargo culted that for a while before I knew it. I didn't know. Anyway, the second thing is I didn't know about walk length. And why would I want to use that instead of just converting the range to an array first and just calling length?
Because you don't have to allocate.
Okay.
So, like, if you have a doubly linked list and you have a container over that, you can just use walk length on it. It's going to iterate through the whole thing. It's not going to have to allocate an array. All it has to do is iterate through it.
Fair enough.
And it is specialized so that if length is defined, it doesn't actually have to iterate. It will just return the value of length. So in generic code, you're generally going to want to use walk length. If it's something that requires length, especially in O of 1, you test for that with has length and use it. But otherwise, you want to use walk length to count characters, and it will be efficient if it defines length and less efficient if it doesn't.
Okay, cool, thanks.
One more.
Yeah, this is more of a comment and a plea because I want to re-emphasize to everyone Jonathan's point about reference type ranges versus value type ranges and the huge complications of having them interact together. I think this is something we really need to work on and think about very, very carefully. And it particularly impacts on things like random number generation, which I'll talk about tomorrow.
Yes, as I could point out, if I can find my example. Technically, this is a slightly faulty example because randgen returns a reference to a value type. So if you did this code twice in a row, you get exactly the same values because it implicitly saves it.
You can also get very nasty things if you start having a reference type range that you then pass into a value type range and you get the mix of reference state and value state that comes from that. So.
It gets a bit mucky, particularly with corner cases, and we're not always as careful as we should have been, and mostly what it comes down to is test, test, test.
Enough of this negative nonsense here. Let's thank Jonathan.